we have already discussed interacting theory. In this week, in this set of lectures, next 3 lectures, we'll be discussing bit about group theory and its representations. So we'll be discussing and we will not go into details, mathematical details of all these group representations. We'll mostly discuss 3 groups. We'll discuss the rotation group SO3, we'll discuss the Lorentz group, which is SO3 comma 1, and then we will discuss the Poincare group. So the topic of this lecture is SO3, which is a rotation in 3 dimension. Okay, so let's consider 3 Euclidean dimension. By that I mean the distance between 2 points. It's defined by y1 minus y2 whole square plus z1 minus z2 whole square. Okay, so this is the distance between 2 points in Euclidean 3-dimensional Euclidean space. Now the question of symmetry is that what are the set of transformations that leaves this distance invariant? Okay, and these consist of rotations along the 3 axes, so this forms the group SO3. So the rotation generated along x-axis is jx, rotation around y-axis is jy and is jz, and then we have reflections along the 3 directions. Axis, and these generators we denote Rx or Z, and this along with, so in presence of this transformation the SO3 enhances to O3. Okay, so we'll discuss basically representations of SO3 and then later representations of O3. So the representation of SO3 is basically this thing you have already learned in your quantum mechanics course. So let's just review briefly. So it has three generators, and the three generators has the following commutation relation. You know this: J I J J J K, where I J K is runs from 1 to 3. Okay. Now, in order to find representations, the thing we defined is that first we define the ladder operators. So they are defined in this way. Okay. Then one can show that the algebra takes the following form. So then a representation is a vector space or a Hilbert space on which the group is realized as operators. Again, you have done the representations, representation theory of angular momentum, and I am just again reviewing it. So the irreducible representation there is a unique, so this element, firstly this J square, it commutes with all the generators. Which means that in any representation, the value of J square is fixed, it doesn't change. Okay, then you can show that in any representation J square takes the value J into J plus 1 times H bar square actually, where J is an half integer. Okay. Then then the basis vectors of the Hilbert space, the basis vector of our irreducible representation can be denoted in this way: J and M, such that J square acting on Jm is J into J plus 1 H bar square Jm, and then Jz acting on Jm is M times H bar Jm. Okay. So this is the way the action of this realized, and then you can show that if this means that when J plus acts on this, this is just simply given by J minus M times j plus m plus 1 j in comma m plus 1, and similarly there is an action of j minus as well. Okay, we also choose these states to be unit normalized, which means j m prime j m to be Kronecker delta j j prime, Kronecker delta m m prime. Okay, so this is basically the representation of angular momentum algebra. So this part all of you have done in your quantum mechanics course. So what we will discuss now is more detailed thing like the representation of reflection. So there are three reflections, Rx, Ry and Rz. So for simplicity we will just discuss the reflection, let's say along the z direction. Okay, so let's consider the reflection along the z direction. So if I take the reflection along the z direction, then what happens to jx, jy, jz, they just go to minus jx minus jy and jz. This is because you know that angular momentum, often people say that this is pseudo vector or something. That's basically the reason for this. So this means that, let's say this is realized by the operator R. So let's say what happens to the angular momentum state under the reflection along the z direction. Okay, so the point is that so let's say Rj equal to j comma m. Okay, let's try to evaluate jz. Okay, jz acting on this is same as, I can write it as rz inverse jz rz jm. Okay, and then this is same as jz because the jz doesn't transform under this. So this becomes an rz jz jm. This means that this is same as m times rz jm. So then basically you see that this vector, when jz acts on that, this is also gives m, right? Which means that jm, rz acting on jm, is simply some phase factor times the same state. Okay, this we have shown now. Now the next thing we can do is that let's now try to do the other thing. So we can try to do then let's say j plus. So then note that rz inverse j plus Rz inverse, sorry, Rz, this is same as minus J plus, right? This follows from just this definition. So then let's try to act this. Let's say J plus, what about J plus acting on Rz Jm? Okay, so this thing can be done in two ways. So one way we know that Rz acting on Jm is simply this alpha Jm, so that means this is same as alpha Jm, J plus acting on Jm, which is same as this factor J minus M, J plus M plus 1 alpha Jm, and then this thing we can do is that we can write it this part as that Rz inverse J plus Rz Jm, which is same as Rz, this thing is minus J plus okay, and this thing is again same as what? So now we act this one first, so this will be same as J minus M times J plus M plus 1, then minus Rz acting on J, sorry, this is M plus 1 because this is J plus act on that. Now Rz acting on this is, so this factor remains the same, alpha J M plus 1 because this is M plus 1, so Rz acting on that, so this is the phase J M plus 1. So then comparing the left hand side, sorry, this must be M plus 1. Comparing the left hand side and right hand side, we get that alpha Jm is simply same as minus alpha Jm plus 1. Okay, so this determines all the phases. For example, we can choose alpha Jj to be 1, and then rest of the phases is determined by the recursion relation. Okay, so this is an important thing. Similarly, so this is we have done. Similarly, one can do R. Similarly, one can do Ry and Rx. See the notes we have done there. But bottom line, this is the way to find the representation of the reflection on the angular momentum representation. So technically, mathematically speaking, this is O3 representation theory. Now in quantum mechanics and quantum theory, we have another important symmetry, which is time reversal symmetry. And we want to understand the action of time reversal symmetry on angular momentum on O3 representation. Okay, so the action of that thing, in order to do that, so let's first take angular momentum generator Jx, Jy, Jz. So under time reversal symmetry, all of them goes to minus. Okay, and from this you can conclude the time reversal symmetry only if T is an antilinear anti-unitary operator. Okay, so this is the statement. That means that what will happen to J plus? So let's take T inverse, and J plus is, so T J plus I Jy T inverse. So this J will go to minus J, Jy will go to minus Jy, but then I will also flip. Okay, which means this goes to minus J minus. And similarly, T J minus T inverse is same as J plus with a minus sign. Okay, now let's try to find the action of the time reversal symmetry on angular momentum representation. So let's say the action of time reversal symmetry on angular momentum representation is Jm is some phase, some complex space times some Jm prime. Okay, let's say for simplicity let's put it Jm. Okay. Then let's first act with so Jz Tjm prime. Okay, so let's first look at the left hand side. So then again we can do conjugation by time reversal, and this will just becomes, this is same as T minus Jz Jm, and this is same as minus Jz as minus T times Jm. Okay, now on this side Jz acting on Jm prime is equal to m prime Jm prime. This implies m prime is equal to minus m, which means that T acting on Jm is simply beta j minus m, j minus m. Okay, this is our first equation. Now we will try to find a recursion relation, and the recursion relation we will try to find, we will try to act with j plus. So if you do this exercise with the recursion relation when we act with j plus and you use this formula that j plus and time reversal conjugation by time reversal gives you minus j minus, then you can show that the recursion relation you get is beta j minus m is same as minus sign is important, beta j minus m plus 1. Okay, so this is a very extremely important equation. So now let's try to do that. So this is this recursion relation. So this means given beta jj, we can determine all the phases. So let's say beta jj is some e to the power I alpha theta, that's the thing. Then you can show that beta jm from the recursion relation minus 1 to the power j minus m. Okay, and if that is true, the important thing here is that let's try to compute what is the value of t square. Why? Because t square is a linear unitary operator, so we can try to evaluate that. So then t square acting on jm is same as t acting on so first we t square is t acting on jm, then t acting on jm is exponential I theta minus 1 to the power j minus m j minus m, sorry. Now note one thing, that minus 1 to the power j minus m is always a real number. Okay, so given that, and then t is an antilinear antiunitary operator, this becomes minus 1 exponential minus I theta j minus m, and then t acting on j minus m, and this thing is same as and now t acting on this is exponential I theta now minus 1 to the power j plus m. All total, if collecting everything, we get minus 1 to the power 2j. Okay, this is a very important equation, t square equals minus 1 to the power 2j, because note that when j is half integer, t squares to minus 1, and this leads to Cramer's degeneracy of fermionic systems. Okay, this is a very important equation, that t squares to minus 1 for fermionic representation, half integer representation, and t squares to plus 1 for all integer representation, t squares to plus 1 for bosonic representations. And you also note that this is consistent with Cramer's theorem, because Cramer's theorem says that whenever there is an antilinear antiunitary operator, the dimension of the Hilbert space must be even dimensional. And the angular momentum representation, so dimension of the representation denoted by j is 2j plus 1, right? Again, it is even only for half integer representation. So this is again consistent with Cramer's theorem. Okay, so this concludes our discussion on representation of SO3, the angular momentum, then further refinement due to presence of deflection and presence of time reversal. In the next lecture, we will be discussing the Lorentz group.